Hello everyone, welcome to the video explanation for Brian Passwater's Topic 2.5 Notes, Example 4. Example 4 follows the introduction of the natural base E, so I left that there so that we can see it. E is seen very often in contextual natural scenarios, so it is a number that we see quite often. So the number of bacteria, B, in a particular culture can be modeled by the exponential function B of t equals 17 times e to the 0.31 t, where t is measured in hours. Let A of t, part A, equal A times b to the t be an equivalent expression for B of t. So as soon as we see those words, equivalent expression, we should be thinking, oh, topic 2.4. Find the value of B. So what we do is we say, okay, well, I'm going to take my B of t, which is 17 e to the 0.31 t. And I want that to match the model above. Well, that means that my base is going to change based on the manipulation of e to the 0.31 t, where I'm going to break that t off using my power rule, and then I'm going to put e to the 0.31 into my calculator, because that value, e to the 0.31, that's B. That's going to be my new base. So I do that, and I get 17 times 1.363. And again, there's some rounding there. We're going to round that answer because it is the answer to this part, to the t value. Okay, so that would be equivalent to A of t, would be our model right there, which means B is approximately 1.363, which is how we answer that question. It says find the value of B. B is e to the 0.31 power, which is approximately 1.363. Part B of this question says find the average rate of change of B of t over the interval from t equals 1 to t equals 7 hours. So I'm going to show you a trick here for using the graphing calculator to do this. What we're going to do is on our graphing calculator, we are going to hit y equals, clear out anything that might be there, and we're going to type in the function from the directions. 17 e, which is right above the division sign in blue, so second divided by e, and then we're going to hit the caret to get up into the exponent, where we're going to type in 0.31 and then hit our variable button. So now y1 has stored our equation. So if we want to do the average rate of change for that function from 1 to 7, we can do that now in our calculator. So real quick, let's write out what that would be in our notes. So over here in our notes, if we want to find the average rate of change for B of t over that interval, remember that these are your x1 and your y1, or I'm sorry, x1 and x2. And your average rate of change which we're not really supposed to abbreviate stuff, but if you use AROC, that's fine. We would be B of T2 minus B of T1 over T2 minus T1, which would be B of 7 minus B of 1 over 7 minus 1. Well, in the calculator, we can do that. All we need to do is get our fraction notation, which we hit alpha y equals and choose n over d. And then in there, we're going to hit alpha trace to get y1, which we want to feed 7, minus alpha trace y1 of 1, arrow down to the bottom, 7 minus 1. That is the AROC value equation. And when I hit enter, it's going to feed 7 and 1 to that equation I have stored in y1, get those outputs, and plug them into this function, which would give us 20.952. So that would be 20.952 would be the average rate of change in bacteria per hour. Okay, then we need to find the number of bacteria B predicted by the model after 15 hours. Remember that this is a t-value. So again, on our calculator, we can evaluate that by plugging it in to our y1 equation. So we go back to the calculator, and we go alpha, trace, y equals, and we feed it 15. And that will print out how many bacteria we would expect after 15 hours. Now when we round that off, remember we can either round it or truncate it. So it would accept 1,777 or 1,778. It does make sense for us to round to the nearest whole bacteria because of the context of the problem.